Hi, y'all. We're excited to have you here. We want to welcome you to Flatiron School's Intro to Data Science, Build Your Own Recommendation System. My name's Corey Mickelson, and I'm the Marketing Events Coordinator here with Flatiron School. A big part of my job is hosting free introductory workshops like this one to give you all an opportunity to meet some of our instructors and get more of a feel of the Flatiron School experience. I also host another event called Tech in 20, where we take 20 minutes to discuss hot topics within the tech industry. A quick little reminder for tonight, we're going to be using the chat as our main source of communication. This is a hybrid event, so it's really important if you put your questions in the chat, we will get to them as we can. So make sure to take that little blue button at the bottom from host and panelists to everyone so we can all chat together. So without further ado, I'd like to introduce our host for the evening, Praveen. He's one of our lead data science instructors. Go ahead and take it away, Praveen.
Hey, thanks, Corey. And hi, everyone. There are some people in person too, and then the massive people on Zoom. So today, so I'm going to be talking about recommendation engines. And so let's just get right into it. I'm not assuming that you have any prior experience with data science, so let's just go for it. So, I mean, what are recommender systems and like in your day-to-day, and how do they like appear, right? I mean, often they're hidden to you. Well, but you probably know what they are by their result in your daily life, right? So what it is essentially, right, it's the algorithmic art of like automating your content, right, curation, right? Like, and getting personalized suggestions, right, based on a whole variety of factors, right? So for example, right, this is happens to be my Goodreads profile. If any of you are familiar with Goodreads. And here, right, I've like, the site I explicitly rate, for example, the books that I've read. And from that, it yields recommendations, okay, based off of my ratings, my explicit ratings. Others are like, I mean, Medium, right? Like I'm sure you're familiar with Medium, right? Basically, based on what I've been reading, right? How many times have I clicked a given article, right? Like I keep going back and reading a specific article, or like how much time do I spend, right? Active time on a website, on a particular article, like reading it and looking at it, right? Well, all of that like user information and like interaction is being logged in real time, right? And that like logging is then being used to be like, oh, if this user spent a certain amount of time, right, interacting with this article, then maybe they're going to like articles that are similar to this, right? At the point that I took this snapshot, I guess I was doing a lecture on NLP, natural language processing. So there you go. Other options, other places where you see these sorts of recommendation engines at play are in product recommendations in e-commerce, right? Right. So based on either recent browsing history on your Amazon, right, or your actual purchases, right? So browsing history being sort of an implicit thing, and we'll come back to this in a second. Or right, active purchases. I actually bought the thing, right? For example, with the case of, this is the case of my viewing history on Etsy, where I, for some reason, was interested in Rest Pro desk lamps and shadow projection lamps and various animistic tribal masks. Okay, so these were basically the things that I was interested in, and the recommendation algorithm in this case for Etsy what also uses, right, not just my preferences, but with using product images, right, item categories and seller descriptions, right, to kind of automate or and content curate for me. So for example, actually, I like this one a lot. Like I was basically looking at these masks and a few lampshades and projection lamps. And sure enough, it started to actually generate content, right, of shadow lamps that looked very similar to the masks that I was looking at, which is actually kind of cool, Now, that's like just a general hoopla, but you're here for actually looking at the recommendation problem, right? So what is the recommendation problem in general? So you have basically in the recommendation problem users, right? Like you, right? You're interacting, right, with a site, or you're rating things, right? And maybe there's a set of users that, for example, a website has, or like, for example, Netflix, where you're rating movies, right? So there's a list of users, and maybe there's also preferences, right? And their preferences, what they like to watch. They've actually explicitly said this for you, right? They've said, right, these are the genres I like, right? And other info, maybe like your occupation might be of relevance, right? Or other things, right? Your age, so on and so forth. So these are all things that come under, users. The other aspect of the problem is items or entities, right? These are just, right, the collections of items that users might interact with. Like for Netflix, it's, well, what is it? You.
What are users interacting with?
Yeah, in Netflix, the movies, right? Yeah, exactly, right? Like, yeah, exactly. That's right. Yeah, yeah, that's exactly right. Streaming content, right? And potentially info on these items, right? So you could have, right, like an expert user, like an expert, right, content curator going in and directly labeling what this thing is about, right? Like that happens with Pandora in particular, right? Where you have like, people who are labeling, oh, it's like, it sounds like this and right? And, again, you have users and items that are interacting with each other. There are different kinds of interactions, right? One is the explicit kind, and Netflix used to have the explicit kind, where you would literally like rate the stars on the thing, right? And so you could be like, 1 to 5 stars rating, right? Or you could do like a like, dislike, 1, 0, so on and so forth. Okay, right? Yeah. Anyway, yeah. But as I said before, right, sometimes user item interactions can be implicit, right? Monitoring user activity and deducing item relevance. Did a user watch a movie, right, to the end, right? Or did a user click on a product page, right? And here the idea is like interaction equals 1, right? No interaction equals 0. Okay, here, right? So for example, here is I'm Praveen. I interacted with a bunch of YouTube videos, like the introduction to Hollow Earth. I didn't interact with this, and then maybe Egypt, right? The Middle Kingdom, okay? And then, yeah. And, for some reason, YouTube keeps recommending me this guy. This guy. Yeah, he's the Ancient Aliens guy. But yeah, this is like the weird side of YouTube. But yeah, like that's that. But basically, they are using implicit ratings most often on YouTube. But we'll focus on recommendations using explicit ratings in this. And I think the main reason why I chose to do that is because it's easier to think about and to talk about. So the algorithm's a little more complicated when you're doing implicit ratings. Okay, so what's the goal? Well, given that you have a user, right, interacting with various items. So in this case, right, a user has interacted with a set of movies, right, and has like explicitly rated them. Okay, so you have like Arrival, gave it a 5, right? So on and so forth, right? And just here's a list of all the things that they've rated, right? And the goal is to like predict user engagement on ratings, right? With entities, in this case, movies that the user hasn't interacted with, right? And then the final part of this, right? Like, so this would be like the prediction. This is like the prediction phase, right? Where you predict what, well, we'll get into that. And then the idea is that out of these things, filter, right? Filter, like basically predict what these ratings might be based on some algorithm. and filter the top K results of the things that have not been seen, right, to get the highest predicted engagement / rating for the user. Okay, so that's just like the basic structure of these algorithms. Okay, so there are many classes of recommender systems, and well, actually, really two major classes, and I'll actually talk about both of them. Well, okay, there are three. The third one is the most modern kind, which are hybrid algorithms, which we won't talk about because that requires some knowledge. So the first kind is called content-based filtering. And the idea here is that, I mean, you can either collect user preferences and info like directly, right, through direct polling, right? So I could literally just come to you and ask you, what do you like, right? And on top of that, you can also get like information from direct interaction patterns with items. But then the key here is that in the database, like you have items, right? In the data, in the item with the items, right? You have a database, right? A database of entities, right? And the idea is that what these entities contain, right? What these items contain, what is in them, right? That's expert labeled and curated, typically in content-based filtering, right? So the idea is that, oh, this is about this genre, this has this actor, right? Blah, blah, blah. Or in music, right? Like, you know, this has like, this is soul, a little bit of soul and this and that, right? And has influences from so on and so forth. And you basically put all of that information into the database, right? Along with the item. So it's the item's info, okay? Now, the thing is that what you really need to be able to do in the end, in order to actually make this a data science problem and convert it from like this kind of talking space into a data science problem, is to figure out how do you represent the users, right? These users and these entities, okay? Movies, for example, in numeric form, right? How do you represent that information in numeric form? And when you do actually represent it in numeric form, the idea is that that numeric representation should encode, right, the item features and also how much, right, like, and the user numeric representation, right, should encode how much the user cares about those features, right? So for example, right, if you have, if a movie, right, is about, if a representation of movies is in terms of genres, right, then the user representation should be something about, okay, how much do they care about each of these genres, right, right, in numeric form. Don't worry, we're gonna get into this. Like, I'll just show it to you. So here's an example numeric representation. So this is Sparkles, and Sparkles really doesn't like Kevin Bacon, likes adventure, doesn't really like horror, likes slapstick and sports, okay, and and then really hates romantic comedy, okay. Now, Free Solo, who knows what Free Solo is here? Yeah. Okay. Yeah. Cool. So it's a movie about climbing, particularly El Cap, and a guy who did it just, yeah, like, anyway, one of the best climbers in the world. And so Free Solo, does this like numeric representation kind of make sense of Free Solo given genres? I'm just like listing in terms of genres, and maybe there's one actor here. Kevin Bacon's not in Free Solo, as it turns out. But yeah. So the idea is that this representation here, right, is based on Sparkle's direct input, could be rather, like, based on Sparkle's direct input, or it could be due to their usage / rating history, right? And you construct that vectors or that representation somehow. And we'll get into how you might do that, okay? The other is, right, I mean, this like tagging right here would be, in the content-based scheme, would be constructed by experts, okay? The list of numbers here that represent the users and the items are commonly called vectors, okay? For those of you who, might know. So here's another example. This is a romantic comedy called He Said, She Said. That's Kevin Bacon. Yes. Yeah. Oh, you're a mathematician. You know the Bacon-Erdos number? Yeah. Okay. All right. It's your degree of separation away from having collaborated with Bacon and an amphetamine addicted mathematician by the name of Erdos. But yeah. Anyway. Yeah. So it is given these numeric representations, is Sparkles likely to like this movie? Just probably not, right? You could just compare the zeros where the zeros and the ones match, right? And it doesn't look like it, right? So this is the idea. The numbers are encoding, right? Some notion of preference between users and movies or items in more general. So the idea is that we can use user and item numeric representations to predict engagement, okay, or the rating. And this is a rather simple, what I just used was a rather simple binary vector representation, 0, 1 representation of users and items. This was just to show you how it works, right? Or how you might represent something. Now, one thing that's really important to know is that users and items were represented in the same space or the same feature space. That means that basically, right, these labels for the features, right, or the kind of characteristics, right, are the same for this and for this, right? Well, it makes sense that it has to be so because you have to compare whether someone will like a movie or not, right? Based on certain characteristics or features or information. So yeah, so they have to have the same dimensionality and they have to correspond to the same things, okay? Both users and feature vectors, the subcomponents of them. So yeah. So Sparkles, in this case, like sports and adventure. Free Solo is about sports and adventure, right? And let's concretely see how these representations might be used to encode user item affinity. That means whether she likes it or not, okay? So I actually just went ahead and, now, if you're not too familiar with the code, that's okay, right? I just created a vector here. Pandas is really a very important data manipulation library that's used all the time. Have both of you? Yeah, okay, good. Yeah, so, and NumPy is sort of like the standard matrix algebra package, okay? And the idea is that I take Sparkles and I encode her, right? As this vector, 0, 1, 0, 1, 1, 0, and then Free Solo. And then this is the he said, she said vector, okay? And I'm just gonna run this. And there's the Sparkles vector, okay? Free Solo vector. And we want to ultimately what we want is a single number that encodes how much Sparkles might like Free Solo, okay? Are there any ideas about how one might do this? Sorry. What distance might be one, or you could do, huh? Yeah, I mean, it's you could use for example, well, I'll just show you, but yeah, the dot product would be a useful way, right? Yeah. And we'll explain what that means. So one way is just to multiply the vectors element-wise and sum the results up, right? So if I did this, right, for example, wherever I multiply and they're not the same, right, it gives me a 0, right? And every time they are the same and 1, that means that Sparkles likes it and that movie has it, it adds a 1, okay? All right. Right. So, yeah. So we're going to go ahead and do this. And so here is Sparkles, right? Here's Free Solo. And what I'm doing is I'm basically just multiplying it element-wise. So I take the element-wise product. And you can just convince yourself this is true, right? If you just take a look at these and compare it to this, this is the element-wise product, right? It's 0, 0. The second one, because Free Solo and Sparkles both, Free Solo is about adventure, Sparkles likes adventure, right? And so on and so forth, okay? And I can just keep going, right? Right? In this case, slapstick was 1, but Free Solo doesn't have slapstick, so slapstick, the product goes to 0, okay? Now I just sum it up, and I get, once I sum it up, I get 2. It's just a number, okay? But it's some metric of overlap, right, between these things, between the movie and Sparkles, the user vector. Now, let's do the same thing with Sparkles and he said, she said, okay? And I went ahead and did this. So that's not encouraging. And I sum it up and it's 0, okay? All right. And so the idea is that, right, if we compare our calculations, right, of these two dot products, or these two of this operation, rather, I'm getting ahead of myself, right? This kind of like, you can think of the higher the number that this number is, right, of this operation that I did between the user vector and the user representation and the movie or item representation. This like kind of numerically encodes the preference, right? So this is like one number that encodes an affinity, right, towards between the two. Is this good so far? Clear enough? Okay. Sorry. Okay, whatever. All right, so now the two operations that we just did are commonly known as the dot product. And the idea is that it generalizes the notion of multiplication to vectors. Like basically what I do is I just take these, like this is the item vector, this is the user vector. I kind of multiply them. This is the same operation I just did, right? And I just basically multiply the components element-wise and then add them all up, okay? That's all. But I'm just gonna keep referring to this over and over again. So building things on top of the other, all right? And another useful notation of vectors in the dot product that will help us later in understanding things is the dot product is often denoted like this, V transpose U. Again, it's the same thing. Oh, sorry, that was messy. And it's often also represented in terms of basically one of these vectors is like transposed this way, and then the other vector is transposed this way. When you see this, you should say, okay, this is like actually this operation is happening between these two representations. So help me out with this one. Can someone tell me what this equals? Sorry. Yeah. 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 Okay. Good. I'm just waiting for someone on Zoom. Yeah. No. That's fine. Yeah. It's 0. It's exactly 0. That's right. That's exactly right. Yep. It's 0. Perfect. Okay. Good. So you guys are like getting it. This is like good. Okay. Excellent. Yeah, because it's 2, 1 times 2 plus minus 6 plus 4, which is 0. Okay, good. Now, given two vectors, we can actually compute this easily using NumPy, so we don't have to like do this every time in our head. So you take Sparkles vector at Free Solo vector, and you get 2. Okay. Same thing with that HSS vector. So it's just this at sign between the two vectors gives you the dot product. And so this operation results, and its results encode our intuition that Sparkles would like Free Solo more than he said, she said. Okay. And the more important thing is, right, like that taking the product more generally, right, taking the product between user and entity vector representations in recommendation systems, right, they yield a measure of the user's preference for entities, right? And this is just generally true, okay? And we'll just keep using this again and again, like. And so you can perform basic recommendations and using filtering on projected ratings, given that the item vectors, right, in a content-based scheme are usually populated by experts. So these V are usually populated by experts. Provided though, we need to have an encoding for U, right? And remember, one way we could have done this is by directly, right, polling like the user, right? Another way, we'll find out another way. Right, so the recommendation procedure is, right, take a set of entities the user has not interacted with, right? So this is like a set, you know, with, yeah. And right now the idea, and so these are represented by these items, right, V sub I, right, are just things that have not been interacted with yet. They're just a set of things that have not been interacted with, right? And then if you've learned the user vector, right, then all you need to do is just like, you can literally just calculate what the projected ratings are, right? Even if, right, I mean, right, like this, you don't have the ratings, right? But these item vectors, right, have been, right, remember, they're populated by experts, but you haven't rated them yourself, right? Right. So, but you know what the user's general preferences of the features are. So when you basically do this dot product, you actually get what the expected ratings, right? What the user might rate this, right, given their preferences. Does that make sense, or is that kind of hazy? Are you good?
It makes sense. Is it like that, like the self-reported preferences are actually reliable? You're saying that, like,
yeah. No, it may or may not be, right? But there's a way to find you, right? Like that's one of the key elements of content-based recommendation systems, right? Yeah, absolutely. I mean, you can ask someone, but it's often better to just like actually see how they've rated other things and figure out what U is, right? Yeah. So that's exactly right. So constructing the user vector, right? So you have your item vectors in a content-based system. And again, they're constructed by expert tagging. But how do you construct a numeric representation of the user vectors, right? So this is the general unknown in a content-based recommender system. Oh, where did it go? Oh, no. Sorry. I think I just, I think I know what I did. Sorry. No. Okay, sorry. I'm gonna have to reopen this. Sorry. I must have closed it by accident. Okay. Sorry about all this. I don't know how that happened. I was here, right? Yeah. Okay. Sorry, I apologize. Yeah. Yeah. So, right, I mean, this is the idea, right? We don't know who Sparkles is, right? And we don't know the users, it's often called vector embedding, right? Now, the content-based recommender problem usually is about finding this embedding given either item, like basically given the item feature database, like the interactions, right? Like what has Sparkles rated, right? Like various products, right? Like this makes sense, duh, right? Like, okay, like, or by direct question. So, right, maybe Sparkles answered all like dislike questions to construct this vector, right? That's one way. Or two, you could look at a history of user entity interactions, okay? And so the idea here is that you have a user, right, that has rated a set of entities, right? Well, we know that this has happened, right? Given the explicit rating scheme, right? And how is the user's numeric representation constructed in the scheme? Well, this is just the inverse problem of what we kind of did before. Before, we were getting projected ratings given a user and an item vector that were populated, right?
Hey,
now, yeah.
They said that they can't, or is your screen messed up?
Oh, can they not see my screen?
All we see is roll call for attendance.
Oh, okay. Well, in that case, hold on, screen. Yeah, okay, sorry about that. So how is the user's numeric representation constructed in the scheme, right? This is the inverse problem of what we did before, right? Before we were getting a projected rating given a user and their item vector, right? Now, right, we want a user vector, right? We don't have it, right? But we have the ratings of like various things that they've rated, right? And we have the expert tagging, right, of what those things are, right? Like of what those items or what those items are. Does that make sense to you? Okay, all right. So let's get a little concrete about this, right? So, okay, I just made a data set, okay. And so here's our data set, and this is an expert tagging, right? So this is like some expert came in and was like, okay, arrival, right, is like is sci-fi, right? And then 0 for all this, right? And so on and so forth. You can go down this and kind of take a look, and this all kind of makes sense, right? Right, thriller, Silence of the Lambs, Gattaca, sci-fi, so on and so forth, okay? So this would be our V's, right? A list of V's. And then these are our movie ratings, right? From like what we had before, right? And I just put it in there. I like so. Oh, actually, I better make sure I loaded this because I preloaded a lot of this stuff. Okay, cool. Huh? Yeah, or somebody else. Yeah, it doesn't matter. But yeah, okay, we can say Sparkles. You want it to be Sparkles? Okay, be Sparkles. Okay. So yeah. So one thing that is useful, right, is to visualize. Let me just make sure. Yeah, is to visualize, right, this user's preferences by features, right, genres and genre combinations, right. And in order to do this, we need to manipulate our data a little bit, right. One thing that I want to like make clear to you is that reshaping data and data wrangling to extract relevant information is like one of the most essential aspects of the data science process. This is for people who are very, very green to data science, like so, yeah. So I'm just going to go ahead and do this because remember, we have ratings, we have movies and ratings, and then we have like basically what the user has rated this movie, and then we have basically each movie and its genres. But we want to maybe figure out some statistics, right, on how the user, given these movies, like what kind of genres they like, right? So there's some manipulation that needs to be done here. Okay. So I just created a handy dandy because not all of you know pandas. That's actually why you should come here. But well, one of many reasons, I don't know. But So what this is going to do is it's going to extract genres for us. It's a little function, a handy dandy function. Don't worry if you don't understand. It's okay. And I went ahead and I ran this. Well, now I ran it. And so you can see, right, I've got my genres, okay, now extracted, right, and in a list here alongside, right, the arrival, right, or alongside these movies, okay? And in some cases, it's two genres, right? It's comedy, romantic comedies, for example, right? Okay. And then the idea is we can group by genres or like genre combinations, okay? And then get the mean rating, okay? All right, cool. And so we see a bunch of numbers. I mean, we can clearly see that sci-fi is the highest, but it's always good to visualize things, just generally speaking. In fact, visualization is one of the best ways to like extract value from data quickly. What can we infer from this plot? What does this user like and probably dislike? Good, that's one. Yeah, exactly. Doesn't like rom-coms, exactly. Yeah, they actually do like Spaceballs. Actually, I'm not even sure if I put that. I might have put that in there just on purpose. But yeah, Spaceballs is great. Keep firing. Okay, sorry. Yeah. Anyway, so our modeling of the inverse problem, right, should reflect what we've seen by simple exploratory data visualization, right? Like this is always a sanity check, doing visualization before you do modeling. So you can always go back and look at what you've done and it's like, does it make sense? Like, there's a lot of times where people like don't do the basic visualization. They don't know where to look and how to tune their models. And also when they get results, they don't question those results, right? You should always look back at your data and have a feel for what the data is. So EDA, or exploratory data analysis, is an essential part of the data science process, okay? And it provides consistency checks on our model. So for modeling the inverse problem, the idea is find a vector representing how much a user weights each feature that best reconstructs the ratings of the movies that the user has already seen. Make sense? Well, oh, that looks ugly. Let's do this as a slide. Okay. Oh. All right, let's do that like this. Okay, good. Remember that the ratings can be defined, right? Each of the ratings that the user has rated, right, can be defined in terms of this unknown vector. We don't know what it is, right? U, and all of the movie items, right? Like that the person has interacted with, okay? Right, and it's a dot product between these, okay? And component wise, right, it's this. Now remember, R sub i's are known, and the item or the feature vectors, right, or the item feature vectors are also known. Sorry, are also known. What's not known is U, right, the user vector, or the user representation. And again, to go back to that nice representation that we had of dot products, but I'm just stacking them now. Okay, so I stack them, and you can see, like, okay, if I take this guy and dot product it with this guy, it gives me R1, right? If I take this guy and dot product it with this guy, it gives me R2, so on and so forth. And doing this stacking, right, creates the entire ratings list, okay? And this stacking of vectors in this way is something known as a matrix. I mean, if you don't know what that is, well, that's like one way to define it. I've done it. There are many other ways, but yeah. And so what we have is VU equals R, where V is the entity matrix, right? It's all, V represents all the information about kind of what the entities are about. Now, this is actually just a linear system of equations for U, okay? And it's typically solved by a procedure known as linear regression. You know what linear regression is? Yeah, okay, good, right? It's a very simple model, right? And what we're gonna do is we're gonna use a statistically robust variant of it known as ridge regression. That's typically what's used in the content-based filtering scheme. That's just actually de facto what's used. Again, that's something that you would learn in like the machine learning phases at Flatiron. So don't worry if you don't know what it is, because you're not supposed to. And the way you do this is by do this ridge regression is by calling scikit-learn, which is basically one of the more important kind of foundational machine learning packages and libraries you'll learn. Okay, scikit-learn. And so, I mean, scikit-learn really makes a lot of this stuff. I mean, like, I used to do this stuff when like these packages weren't around, and it was painful. Now it's like really like dot fit. Okay, so I'm importing Ridge. Ridge is basically the model that we'll be using. There's a bunch of other stuff that you don't need to know about. Train test split is important. Okay, and the idea is, and why I imported it is also important. So typically in a learning algorithm, part of your data is going to be used to fit the prediction algorithm, right? Like the idea is that I want to like actually like get those U values, right, in some way, right? But then the question is my like representation good, right? Is it like statistically robust? Does it make sense, right? So like the idea is that you take a small chunk of that data and you keep it in test, right? Like, and you set it aside. You basically run you basically train your data, you fit your model, and then you basically predict, okay, on the test set, okay? And you look at what the actual values of the test are, you compare the two, okay? And we'll see that in action. Now, the whole idea here, this is just a flow, right, of what might happen. So you have your data set, you do a train test split, right? So you have a training set and a test set. Here, you fit the model, okay? Then here, basically, you evaluate the model, and there's some metric that we'll use to evaluate the model. And if it's good, great, and we can move on with confidence, okay? And predict on things the model has never ever seen before, right? I mean, right? Or that you don't know that you don't know what the answer is to, right? Like, that's the better way to say it. So in order to do this, you do the train test split, and this is basically, this right here will correspond to my movie features, my entity features in the train set. This is in the test set. Then these are my ratings that I'm going to use in the train set, right? I'm establishing a relationship between the train variables, like between the ratings, right? I'm using this, and then basically the movie features, right? And then basically this will be used to kind of evaluate how well, at the very end, how well my model, my user representation is doing, okay? So again, don't worry about all this stuff, okay? So I'm just basically defining the model, and I'm fitting the model to the training data, okay? Then the fit coefficients of this model. So actually, this is all it was. I literally just fit the model, okay? So it's like really, really easy, okay? It's really fast. It makes your life really painless. And there's like, actually, the way I did this with this thing called a pipeline is a way to really professionalize your workflow as your models get more and more complex. Are any of you familiar with pipelines at all, or?
When you say pipelines, do you mean like data pipelines or something?
Well, modeling and data transformation pipelines. Yeah, so it's like part of the whole process. Yeah, exactly. Yeah, exactly. So this is what that is. Okay, that's good. Exactly. And this is like what you should all be. What by the end of like Flatiron, you will know how to do this professionally. All right. So I fit it. And this is my user representation. I've got it, right? That's Sparkles or whoever, okay? And this is basically the coefficients that represent her interests right, in this space of genres, okay? So let's predict on our test set and see how it stacks up against the actual rating. So in order to do that, I'm just going to go ahead and, again, this would be the same thing. So I take my test set, right, which is basically this, right? It's like, it just happened to be Arrival, Star Wars, Return of the Jedi, and Vertigo, okay? And, you know, Vertigo is a thriller, you know, Arrival and Star Wars are sci-fi. And this dot predict method is, again, it's basically I'm predicting what the ratings should be given these features, given these movie features. Okay, is that clear to you? Okay, all right. This is the same thing as what I was doing when I was multiplying the dot products, right? I'm doing the same thing here. I'm basically multiplying. This multiplies the feature vectors with my newly found user vector. Okay, and now I get the predictions and I compare it against the test. What do you all think? I mean, it's a small sample size, I know, but this is education. It's meant to be illustrative, not. It's good, right? New message. Let's see. Yeah. Yeah, and it does actually, like it does, but actually one of, I'm about to get into that in a second. But first, before I do that, so yeah, it looks good. And generally what you do is you evaluate this type of content-based recommender system, just like you would any kind of linear regression, right? So what you want to do is you want to test the predicted ratings against what the user actually rated them in the test set, right? And for our purposes, an error metric like the root mean squared error is a good way to do this, right? Where you basically sum over the test value, the actual values of the ratings, subtracted by the predicted values, what you predicted, square it, divided by the number, the total number, right, of values, of a total number of observations in the test set, then you take the whole square root of it, right? And that gives you the measure of the error. And so I go ahead and do that. And yeah, that's pretty good, right? I mean, right, if you're like rating from 1 to 5, right, and you're getting like 0.5 this way and that way, that's not bad, right? That's not bad at all. That's not shabby. Yeah. And so the final step of this whole process is making the actual recommendations, right? So in the end, what you want to do is you want to look at a database of items that the user has not interacted with, right? So far, we've actually been looking at things that it's interacted with and tested whether our user representation is good. And remember, the features have already been labeled by the experts. And what we're now going to do is just use our user representation to predict the rating and the rankings of in the entire database of things that user has not seen, okay? So here are a group of, so here's a bunch of stuff that the user has not interacted with, right? Free guy, the big sick, don't mess with the Zohan. Okay, right, everything, everywhere, all at once, okay? And what I'm gonna do is basically take these and put it into our model for a prediction, okay? And then just predict, right? And so you can see that, okay, like everything, everywhere, all at once is high, moon, which is another sci-fi, is high, so on and so forth, right? And what I'm going to do now in this process is do the ranking step, right? This is the last step, right? So I basically sort the values, and then usually, right, you're not interested in everything in the database, right? You're interested in only the top X or top K or whatever, right? And so you just go ahead and get maybe the top 3 for a user, right? And so given our user's profile, this makes sense. Doing everything, everywhere, all at once, and okay. But this is like, I mean, yes, I'm using a toy data set, but this is the exact like principle, and it would scale, right? This, in fact, this entire architecture is actually how you would do it, right? In the content-based scheme. Now, the idea is that, right, so just a summary, right? So just to finish off, right, with this. So you have item characteristics, right? These are features that get encoded by experts, right? And then the idea is that you learn which of the features the user cares about, right? Based on their ratings of things, right? And then you predict and rank, right? On the item database given user rating, given the user vector. And there are, now, what are the pros and the cons, right? This is very simple, like relatively speaking, in the world of algorithms. But the pros are, right, is that the algorithm is, well, very easy to implement. It's like 3 lines of code, right? But the most important thing is that it can work even with limited amounts of data. A lot of the modern recommendation systems require a ton of data, right? And oftentimes, and they work really well in that regime. But when, for example, you have users that are new, right? And you have a small company that's just starting up and you're doing ratings and you're trying to get, basically building your interactions, right? You might actually have pretty good expert ratings, right, on the products you offer, right? For example, right? Because, you can pay attention to put a lot of resources and figure out, okay, this is what this is about, blah, 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 or you're labeling those things, right? But you don't have that much information, right, about user behavior, right? But you're learning, right? And the idea is that in this small to intermediate regime, in the smallest regime, you would just label the users, right? And their vectors, right? And then, right, do content and then do the recommendation. But as they maybe interact 10 or whatever times, all of a sudden now this modeling approach actually starts to get pretty decent. Okay, and this is this regime where other more fancy algorithms don't work. So this is where you would actually practically use this. Okay, is that clear, more or less? The cons are pretty huge though. The algorithm is only as good as the selected features, right? That means I'm an expert, you need good experts, right? And that costs a lot of money, right? You need expert labeling for the features for each single item in your database, right? Obviously, as you get to huge amounts of content, this is impossible, right? And this can get very expensive and time consuming to acquire, right? And you may not even be able to do it in principle, right? So there's another approach to this that scales to that larger regime, okay? And that's called the collaborative filtering approach. And the idea here, right, is, okay, if I have a lot of data, maybe I have tons of users, right? And a lot of interactions, right? Maybe you don't interact with a lot of things, but okay. Now, the idea is that if I have a user here, right? Homer donut. Okay, sorry. Yeah, he likes donuts and pizza, right? He likes, right, donuts and pizza as well. He's never had a bag of potato chips, which is pretty hard to believe, but okay. And then the idea is that, right, Homer has had a bag of chips, right? So the idea is that since these guys, like their interactions, right, what they've bought or what they've liked, right, are similar, right? Then the idea is that you recommend things, right, based on their user profile or usage history, similarity, right? You recommend things that maybe this guy has tried that he has not, right? So this is the idea of user-based collaborative filtering, recommending items that users similar to you like. Another option, right, is recommending items, right, that often appear high up together in people's preference lists. Right? So this is the idea of item-based collaborative filtering. So for example, this person likes, may like a whole bunch of things that the other ones don't like, but like this one and this one, right? Grapes and watermelon, right? This person also likes, but maybe different things than you two and you one may have actually quite different preferences, but for some reason, right? If they like grapes, they like, right, watermelon, right? And so the idea is that grapes and watermelon keep appearing together over and over again, right? So maybe there's I don't know, this is like a really, I don't know why I use this example, but like, because grapes and watermelon are not similar at all. Like, anyway, whatever. Yeah, but like, imagine that they are, okay? Then maybe you might assume, okay, there's like some similarity here, right? Between these things, right? Based on the fact that, right, they keep appearing together. Now, one of the key points behind both of these, right, types of collaborative filtering methods, collaborative recommendation systems, is that only user IDs and item IDs, there are only user IDs and item IDs in the database, right? And there's no other information about them apart from their user rating, like right there, like item user interactions, right? Like that's it, what they rated, right? You don't have any expert like content curation, nothing, right? You don't have item, like you don't have user information about like, who I am, right? Like just what they've rated. And this is key. And so that's nice, right? You don't have to content curate. And the idea is that now what I'm going to do is I'm going to motivate and implement a method that actually, like traditionally, like traditional methods you would either use item-based collaborative filtering or you would use user-based, based off of something called neighborhood approaches. If you don't know what that means, that's okay. But the idea is that we can actually use some of what we've learned already to do both items and user-based collaborative filtering in one shot. So we can do both at the same time, okay? And using only the user item interactions. Now, the general idea is we want to estimate preference on all items that the set of users have not interacted with based on what the set of users have interacted with, okay? In general, right, that set of all user item interactions will form a matrix. So here's an explicit rating matrix, okay? Some users, items. Now, the key point here is there are a lot of missing values, okay, right? But there are things that, yeah, like, I mean, in general, right? Like you haven't watched, like if you're Netflix, right? Like the user has not watched like a huge fraction like, of right? Has only watched a small fraction, right? Of the movies, right? In the database, right? So there are gonna be a lot of missing values here, right? But this is exactly what we wanna predict, right? Like this is actually the things that it has not, you have not like, that you want good predictions for, rank them and recommend them, right? So the goal is to ultimately impute these missing values. Impute means fill in, okay? For those of you who don't know. And basically get a prediction for items that a user has not interacted with, right? In a way that reflects what similar users like. And in a way that also reflects the items that are similar to the given items, okay? So it's like both user and item-based filter. But how do I do this, right? I only have the user item interactions, right? And actually, I have an unknown, my user representation is completely unknown. My item representation is completely unknown, right? And if I want to build up the ratings in the way that I did before, right? I need both, right? In some way, right? But now I don't have one or I don't have the other, I have neither, right? Like, but maybe I can use the observed user item interactions to get a representation for both in one shot. And that's why I went through all that content-based stuff also, is because it sets the stage, right, for this, right? So the idea is something known as matrix factorization, right? And the idea here, similar to what we did before, right, is that this is a vector that's unknown. This is a user vector, okay? This is an item vector. When I take the dot product between them, right, so this is the second row, this is the second column, I get this of this, I get the second row and second column, right, element, right, which is the rating, right? And so that's what this dot product represents. So these are matrices, U and V. U represents the users, right? Each of these rows represents a user representation. V represents the vector, represents the item representations. The columns represent the item representations, okay? Now, one key point is that, so first, this is what's known as a factorization, right? Because what I've done is I factored R, the rating matrix that I've observed, right? With a lot of missing values. I'm attempting to factor it into to a multiplication of two matrices, right? One being the users and one being the items, okay? And now you may ask, this D, right? I have to choose D, right? D is like the length of this. In this case, it's 2, right? It's the length of the representation, right? Remember, the length of the representation for the users and the items have to be the same, okay? We talked about that earlier, okay? But choosing D is actually one of the principal problems in this, right? But oftentimes, you can get away with, anyway, we'll usually you fix D and then you run this algorithm, right? And you get a representation. Okay, yeah.
But D is the number of features of the items.
Yes. D, good. D is the number of features of the item. It's also, right, then the number of preference features for the user. Okay, yes, exactly. And they have to be the same dimension. Okay. And again, that's something you fix when you run it. And then typically to optimize, you iterate over different values of this and get the best representation length. Now, the idea is that you use what items have been rated in the database of users. And then the idea is that you learn the item representation and you learn the user representation, but you have to do this iteratively because these are both unknown, right? And so one way you can do this is, and this is actually what the algorithm is you initialize U randomly, it's just a bunch of random numbers. And then you do a linear regression, just like we did before, to find V, to find these vectors, these items. And then, now that you have that, you go back and you solve for U given the V, right? Remember, we solved for U before, right? In the content-based. And you just keep doing this. You keep hopping back and forth. You keep doing this, iterating back and forth, right? And you play this game until the user and item representations converge and minimizes the difference between these dot products and the observed rankings, i.e. the ones that have actually been observed, okay? Just as a side note for all of you, these algorithm implementation is sometimes called alternating least squares. The linear regression that we use for the content-based is least squares. So yeah, here it's alternating because you're solving one problem then the next and you're going back and forth, okay? It's also sometimes known because a lot of these algorithms have probabilistic interpretations, and a lot of statistics and probability theories lie underneath data science. So it has, it's sometimes known as probabilistic matrix factorization. And another version of it or iteration is called Simon Funk's SVD. That's the one that won the Netflix prize in 2014 or something, and which they basically adopted and made a lot of money. That's the one we're going to use, okay? So what is the result of all of this in plain language, okay, right? Okay, yeah. So we've iteratively found an item representation, okay, in terms of the observed user-item interactions and user representations. And we've done this vice versa. We found a user representation in terms of the observed user-item interactions and the item representations. Remember, we're solving this problem back and forth. And as we converged, right, similar item representations, and so as we converge, right, similar item representations start to become defined in terms of users that are similar to each other, okay, and their rating profiles, and vice versa. Similar user representations defined in terms of similar items, and how they were rated across different types of users. Okay, this just happens to, you can show this starts to become true as it converges. And that's why it's called collaborative filtering, because in the end, right, you're using all the users in your database to like learn what the features are, but the features are a reflection of what similar users like in the space like, okay? And so what is the result of all this rigmarole, right? So the idea is, well, we'll see. The idea is that once we get all the users and all the like items and the representations, the U and the V, and fill it out, we actually fill out the U, yeah. Well, okay, so we do it to reproduce the observed values, but something else happens. So here's an example, and I'm going to show you what it might look like, right? So here's the user item ratings, right? Like these are items, I mean users, these are items, okay? And you can see there's like some missing values here. Now, the idea is, oh, sorry. Now, after running matrix factorization, right? Now I decided to just choose a dimension of 2, right? The users might look something like this. So user A, B, C, and D, and their features, and their feature vectors. And here's the items, okay? And this is after the result of SVD, of doing this like iteratively, right? So these are W, X, Y, Z are the items, okay? Now, this is what happens when I multiply the users and the items matrix together. Oh, no. Sorry. I'm so sorry. Hold on. I forgot to run all of this stuff while I was doing it. Okay, we're good. Yeah. And now let's compare this to the actual user, the observed, right? Does this look good? Compare. Donut. Yeah, right? It's actually right. Look, 3.163, right? For the observed values, right? 2, 2.22, right? This is 3.183, right? Okay, so it's starting to match up 1.5, 1.48, 3.95, 4, right? But I also have something else. What else did I get when I did this? Yeah, I got the predicted values too. I got my matrix filled in. Okay, right. The factorization attempts to approximate the observed values, but it also finds missing values that are likely or probable under the observed values. You can actually show that rigorously to be true, by the way, using probability and statistics. And these values that you filled in can be used for recommendation. Okay, you've done it. Okay. It also finds the hidden representations of users and items at a given dimension that you specified, which is D. Sorry, it got cut off here, but.
Ask a question.
Yeah.
So just to clarify, the numerical values associated with the items that were multiplied in this matrix are based on actual ratings, or could be based on anything?
What?
You're using ratings as an example of what they're based on.
Wait, sorry, I blanked out for a second.
So you go back to one slide.
Yeah. Oh no. Oh, sorry. Yeah, which one? Here?
So yeah, so the right side, the XYZ.
This one here.
Yeah. So those what are those numerical values represented?
Oh, they're represent these numerical, great. So these numerical values are representative of features. But you don't know what those features are. Like they're like, so this is 1.5, this is 1.7, right? This is like, but what it is it's like representing in like a hidden space, like kind of, it's what it's representing is sort of a part of the space in which certain sets of users live in. Does that? This is items. I know it sounds weird.
Based on like interactions on the
Yeah.
website. For example,
Yeah.
or
Yeah.
items per-
Yes.
It's based on true events that happen.
Yes, absolutely. You find these and it's based off of true events that happen and sectoring the space, right? And figuring out what sectors of the space that this belongs to. Yeah. So you're actually, but that like representation in that space is hidden from you. You discover it as you go, right? Yeah. By this factorization technique. Is that? It's not clear. It shouldn't be clear because it's not. That's the one of the things, right? These features are often not interpretable. They're not human interpretable. Yeah, exactly. Like sometimes they are. Like when you're like, oh, okay, yeah, that actually corresponds to like someone like with horror, right? But oftentimes they're just like, I don't know what that means, right? Which is a lot of machine learning, by the way. Yeah. Exactly. Yeah, that's right. That's right. Cool. All right, so yeah, I have like, all right, good. I actually have enough time, maybe. So fortunately, we don't have to usually implement this by hard coding again, this like sort of iterative algorithm. They're a really nice pack. Well, I actually don't. It's not a great package, but it's an okay package. But it'll do the job. And for collaborative filtering, and it's called Surprise. It's like a modification of scikit-learn specifically for doing recommendations. So if you're doing any kind of recommender system and you want something that's very like simple to use, like Surprise is like a nice way to get up and running. Okay. So Surprise has a bunch of things that you need to like load the data in a specific way, and it parses the data in a specific way. So this data set and reader does that. This is the algorithms. Remember Simon Funk's SVD, right? So this is like we're just importing the SVD algorithm or model, and then we want like maybe some metric. We could say the accuracy, which in this case is like the RMSE or the root mean squared error. Okay. So that's like a way to test metric. And then just like always, right, we want to do a train test split, right? Because we have our observed ratings and then, what's left. Well, we have observed ratings and we want to like test against like some set of the observed ratings and see if it's working. Okay. So here's the data. Oh yeah, I forgot to put a picture up. This is this data is from the Movie Lens 100K rating set, which is like 100,000 movies, and what users have rated them. Okay, or no, not 100,000. Sorry, incorrect. There are 100,000 ratings. Yes, and there are 9,000 movies. Yeah. Okay. Yeah, that's better. And about 700 users. Okay. Sorry, my bad. Yeah. Good. Yeah. So there's about 100,000 or so ratings, which you see here. And I've just loaded that in. And so you can see here you have user ID, movie ID, rating. That's it, which is all we need to do collaborative filtering. And remember, we need to get the names of the movies as well. And the idea is we can link them to the movie ID. So that's like in a separate data like thing. I just like ported it over. Again, don't need to know, like this is the movie ID, Rocky 3, so on and so forth, okay? And like, again, like an important part of being a data scientist is like taking different disparate sets of data, and he would know, right? Data analyst, yeah, that's like, yeah, and like merging them and like stitching them, record linking, and like, yeah, okay, it's a lot of work. and it's painful, and will be your bread and butter. Okay. Okay. All right. Now, that data doesn't look in the standard form for user item interactions that we had, because it's just a list, right, of ratings and like whatever. Now, it's fine to use it. Surprise takes in that data in that form, so it's fine. But just to show you something that looks familiar, I went ahead and like basically put the movie ID as the column and the user ID as the row. And you can see here, here's a matrix, or like at least 5 rows of the matrix. Yeah. What do you notice? Yeah. A lot of empty values, which is quite typical. Most of your matrix will be empty. Actually, this is called a sparse matrix. Okay, sorry. And now you have to get the data ready for surprise. Hold on, we got questions here. Okay, cool. So surprise can take in pandas data frames and load the data into its own. It has its own internal data structures. And so you can go ahead and do that. Basically put the data frame. We want the user ID, the move ID, and the rating. And then you basically load into a data set data structure with this reader, which basically says, oh, this thing is coming in the form user, item, and rating, right? Like it just teaches it how to parse it properly. Okay. Now, we should also do a train test split on the data, right? Just like we did before. I'm going to do an 80-20. So, what? Oh, what happened here? Sorry. Let me just make sure I have everything. Okay, good. All right, cool. All right, it's done. Okay, so it did it. So now it basically split into a train set and a test set, okay? And now what I'm gonna do is do the modeling. And this is, we're gonna use, again, Surprise's implementation of Func SVD, and I'm gonna use a representation length or a vector size of 15. That's D equals 15, okay? And you can fit it with just the standard dot fit method. It's that simple. So I've defined some other parameters which just happen to make it work well. And then I'm running, what I'm saying is I'm running this iteration back and forth 80 times, okay? Like where it's doing this kind of solve for U, then solve for V, then solve for U, then solve for V, okay? And again, n factors is D, 15, okay? And when I go ahead and do that, it's gonna take a few seconds.
So you like iterate yourself to determine what the right years were?
Yeah.
But there are programs that can just like tune those for you.
Yeah, I mean, so actually, like, there is a hyperparameter tuner, what's called hyperparameters. These are hyperparameters or like input parameters. There's a tuner within Surprise to do that for you. I just didn't do that because it takes long.
Which would produce the right values to maximize some like
objective function. Yeah, exactly. Yeah, exactly. Like an evaluation metric. Exactly. That's exactly right. Okay, so it's done now.
Someone's asking how you chose D15 or D15.
Because I have skills. Okay. No, I don't know. I just chose it. like honestly, like I mean, as we were saying, the principled way of doing it is to like actually test, like to iterate on the number of dimensions and like test how your like model is doing, right? On tests on a validation, what's known as a validation set, okay? That's like the way you would do it, like in principle. I'm not trying to be blasé about that. That's the way you would do it. So I could have maybe have gotten away with 10. Maybe I could have done better with 100. I don't know. So now predicting on the test set, right? So the test set is data from which we have the true value ratings, the rating values, right? And the idea is that we can compare, right? So what I do is I take the SVD object, which has been fit, right? I fit it. And with the train set, and now I do this .test method on the test set, which I split, okay? And then I can call, and then that outputs some predictions, okay? And then what I can do is I can look at the predictions, right? I.e., what this algorithm has predicted for the matrix, right? I mean, for the user ratings matrix, and look at its root mean squared error with respect to the true values. Okay, and when I do it, I actually don't know what it would be. Okay, it's 0.88. Okay, or some 0.89. Now, is that great? I mean, maybe not. I don't know. Like, the question is what you want, right? Do you want to like predict the number of the rating well, or do you want to, is the goal to like, I mean, how much do those numbers mean anyway, right? What's the difference between a 5 and a 4 and a 4 and a 4.5, right? Like, probably not all that much, right? But like, there's maybe big differences between 5 and 2, right? Like, or anyway. So maybe this is fine, right? Ultimately, the goal was to get the best recommendations, but this is just, for 1 to 5, 1 to 5, yeah, 1 to 5.
So that 28 is across the 15 features that you chose.
So this 0.88 is across the 100,000 example. Yeah, or in this case, 20% of 100,000.
So none of this is the prediction.
Yeah, it's the exactly. It's the prediction and comparing it against the test. Yeah, good. So it's not actually too shabby. And remember, like, we're talking about like, right? I mean, now we're talking about a huge user database and like complex, right, movie like features, right? Or like movie, and we're like discovering features, right? So this is not bad at all. And so let's compare the predicted to the actual ratings. So here are some examples. So RUI is the actual rating, and this is the estimated for some bunch. What do you think? I mean, all in all, it's pretty damn good. Like, I mean, so this is how it works, okay? I mean, at least this is how you deploy it, right? I mean, like, do this. I mean, okay, you might be like, hey, man, you only like showed me 10, like you're cherry picking, but now the idea is, okay, now like these are on the test set. Now I want to evaluate the estimated rating of a user for a single item, let's say. I could do that too by basically taking a given user ID and a given item ID, doing the predict. And in this case, I chose one in the database where there was none. There was no rating whatsoever, right? And it gave me an estimated value, okay? And now you can also get the user's vector representation. You could do the same thing for features as well. I'll just do it for, so the fifth guy. So this is the vector representation, right, for user 5, okay, which we found. And you can print out the length, and it had better be 15, which it is, okay. And in general, now, like what we want to do, I think I have top 5 recommendations. Anyway, you want to recommend a top n number of recommendations for a user that they haven't interacted with, right? To do this, like, actually, unfortunately, this is why I don't like Surprise that much. It requires a little bit of coding, which I'm just going to go ahead and do. And it's also kind of slow. So here, what I'm doing is I'm basically given a prediction for a set of users. I get the top n ranked for each user. And that's what this function does. And then what this does is it builds a set of user item interactions that have not been observed. So this is from the train set. And then I basically predict on those non-observed, only the movie, like the movie user interactions that have not been observed, right? And I predict only on those because that's what I want. And then what I do is I order and rank the top 5 for the users that have not, or I think top 5. This may take a little while, unfortunately. Well, okay. Actually, I already have the results from before. So what I did was I went ahead and for user 5, their number 1 happened to be Galaxy Quest, which if you have watched, like Raptor's hammer. Okay, I shall avenge you. Okay, anyway, but yeah, so that's kind of how it works, and I hope that that's all I really have to say, and I actually ended right on time. Wow. Okay, I did. All right.
Thank you again to Praveen and everybody else who joined in tonight. If you have any questions about Flatiron School, I'm going to drop a link to schedule a chat with admissions, as well as our YouTube channel. That's where we post all of our events after we send them out to y'all. And then a link to our events channel or landing page. That way, if there's any future events you want to sign up for, you will have it at your fingertips.
All right.
Yeah, we'll be sharing the slides too, so everything will kind of come together. I'll make sure that we have that the code somewhere in the slide deck or on a separate link, and then we'll have the video along with there as well.
All right. Cool.
Okay, thanks everybody.
All right.
Have a great night.
Bye. Bye all.
Bye.
Thanks for joining. Bye.